Good evening, Lamai. Let's start the session for today. Right. Today we are going to discuss about the hybridization and the orbital overlap. Right. That is going to be the major focus today. Right. Okay. Actually, these concepts, the hybridization and the orbital overlap, those concepts comes with the theory called valence bond theory. Right, these things comes under a theory called valence bond theory. Right, first of all, let's discuss why we need a different theory than the Lewis theory to completely identify the molecules existing in nature. Right, so that is our major task now, to clearly identify or get the total idea of molecules existing in nature now. So to get that clear idea, the total knowledge about the molecules existing in nature, right, the Lewis theory is not enough. Right? What are the reasons why we need a new theory rather than coming up with the Lewis theory? Let's discuss about that thing first. So basically, when it comes to Lewis theory, actually which is actually created with the use of the Bose model, right? Actually, the foundations of the Lewis theory, right, resides with the Bose model, right? The 288 model. With that also, we came up with the Lewis theory, the octet rule and the stuff. So the Lewis theory is basically based on the Bose model, right? But nowadays we know, not like in orbits in Bose model. Nowadays we are with orbitals. So we need a theory which based on orbitals to describe the molecules existing in nature. So major difference when it comes to orbitals is orbitals giving you a 3D idea. Orbitals coming up with kind of a 3D nature, right? But not the orbits that much, right? So the bonds are formed three-dimensionally, right? Those can be described with the use of concept of orbitals with the new theory. So, but Lewis theory unable to describe, right, the bonds in 3D form. So Lewis theory and the Lewis structures are kind of diagrams, right, written in papers, 2D theory, right? According to Lewis theory, right, industry is written like this, kind of a 2D theory, right? Looks like the angles between the bonds basically 90 degrees for Lewis theory. Which is a 2D theory. But the existing industry molecule is with kind of a bond angle, right, which is equal to, right, 106. That kind of bond angle, not the 90 degrees. So some 3D forms. So one bond is towards us. So one bond going towards into the board. That is how the existing industry looks like. right? One is at the same plane, one is coming towards us, one is going into the bond. That is a 3D NH3 molecule, the 3D molecule, existing molecule. So Lewis theory was unable to explain the bonds in three-dimensional space, right? As it's a 2D structure. So that was one failure with the Lewis theory, and one need of a new bond, new theory to explain the bonding. The second thing, right, is actually when it comes to Lewis theory, if you think of the Lewis theory, and let's see, CO2, according to Lewis theory, CO2 looks like this, right? The two bonds, Lewis theory, both the bonds, so you see, is one bond and second bond. Both of the bonds between the carbon and oxygen looks like the same according to Lewis theory. If you are coming up with dot pro structures, dot structures, or dot dash structures, these two bonds looks like the same according to Lewis theory. But when it comes to 3D diagram or naturally existing CO2, these two bonds are different. One is with a greater strength than the other. One is stronger than the other. Three-dimensional arrangement of bonds differ, right? But those things can't be explained with the use of Lewis theory, which is a 2D diagram, and we choose the Bose theory. The foundation of Lewis theory coming up with the Bose theory, orbits 288. But naturally existing structures are 3D, right? So we need a new kind of a theory. We choose the new atomic model, which is known as the cloud model. So the new theory, the valence bond theory, actually based on the cloud model, right? Today's model. So that is the importance of this theory. And this theory is able to explain the difference between these two bonds. Why one bond is more stronger than the other thing, right? And explain the 3D arrangement of these bonds, these two bonds. This is able, the valence bond theory, right? So today we are going to discuss about that thing, right? So in your note, it is said as the first point, Lewis theory doesn't give any explanation on how the bonds are formed in three-dimensional space and why the sigma and phi bonds are different. So these bonds are named as sigma and phi. According to Lewis theory, no such thing, right? Both are same, but actually we know these things are different. That is why we have given two names, sigma and phi, and those will be discussed with the new model. We choose the cloud model, the new theory, valence bond theory, right? And the second point it says, right? So when it comes to Gauss theory or the Lewis theory, right? The formation of bonds is actually by overlap of orbits, right? Actually, when two orbits are overlap, like this, if you are to form the HCl, when hydrogen's orbit connects with the chlorine's orbit like this, then the bond is formed. This is how the bonds are formed according to Lewis theory, right? These are orbits, hydrogen's orbit, and this is the chlorine's orbit. orbits will share their electron pair to form the covalent bond according to Lewis theory, right? But according to our new theory, the VBT, the valence bond theory, which is a 3D theory, it says overlapping of orbitals, not the orbits like this, not the sharing electrons of orbits, overlapping of orbitals with 1s orbital of hydrogen, 1s orbital of hydrogen, when it is to overlap with 3p orbital of chlorine, when it is to overlap with the 3p orbital of chlorine, when it is to overlap like this, that is how the bond in HCl forms. According to the valence bond theory. That is the difference between the two theories. Here the orbits share their electron pairs to come up with the covalent bond. Here the orbitals, the 3D concepts, orbitals will overlap to form the bond between H and Cl. That is how the two theories describe the formation of the bond between H and Cl. This is the acceptable model now, because nowadays we know the cloud model is used, 3D model, not like this. So we are going to discuss about this theory today, right? How a covalent bond is formed according to the accepted model, cloud model, right? So that is described by the valence bond theory, right? So with the second point, it is said, see, go to the note, it says, right, valence bond theory states that the covalent bond between the two atoms is formed by the physical overlap, of halfly filled valence orbitals from each atom. When halfly filled, 1 electron each, right, halfly filled valence orbitals are to overlap with each other. That is how the covalent bond is formed according to valence bond theory, right? Okay, so these kinds of overlaps according to valence bond theory are of two types. According to valence bond theory, the orbital overlaps are of two types, right? VBT, valence bond theory, VBT means valence bond theory, right? Orbital overlaps are of two types. What are two types? Type number 1, right? When orbitals overlap, inside the or on the internuclear axis, right? When orbitals are overlap inside or on the internuclear axis, there is one kind. Such orbital overlap is referred to as a linear overlap. And a bond, valence bond, and a covalent bond formed by a linear overlap is referred to as a sigma bond. That is the first kind of overlap, orbital overlap possible according to the valence bond theory. See some examples. right? If some 1s orbital to overlap with another 1s orbital like this is what happens with the H2 molecule, right? 1s of hydrogen will overlap with another 1s of another hydrogen, right? This overlap occurs on the internuclear axis. This is the internuclear axis. Internuclear axis means the axis which goes through the two nuclei. This is the internuclear axis. When this overlap occurs on the internuclear axis or inside the internuclear axis, such a bond is referred to as a sigma bond. Such a bond is referred to as a sigma bond. And this kind of overlap is referred to as a linear overlap. Right? So this is the sigma bond between the two hydrogens. 1s orbital of hydrogen overlaps with another 1s orbital of hydrogen. Linear overlap. If you need some other examples, see, in HCl also we see the same kind of a overlap. Hydrogen's 1s overlaps with chlorine's 3p. So again, it's a kind of a linear overlap. See, the orbital overlap here, the orbital overlap occurs on the internuclear axis, or inside the internuclear axis. These are referred to as sigma bonds, right? So sigma bonds can be made by overlap of all the kind of orbitals, overlapping of s orbitals, overlapping of s and p orbitals, right? Even overlapping of, right, s and hybrid orbitals, like this. Some ns orbital and sp, sp2, sp3 kind of hybrid orbital. Still linear overlap may occur, can occur like that as well. So all the kind of orbitals are involved. All the kind of orbitals can involve in forming sigma bonds like this. Can generate some kind of a overlap inside the or on the internuclear axis. Even pp guys, no? Even p orbitals, two of p orbitals can overlap linearly. See, in Cl2 you will see this. When forming Cl2 molecule, this is what you see. Overlap of two orbitals on the internuclear axis. The 3p orbital and the other guy is 3p orbital. Again, this is a linear overlap and referred to as a sigma bond. Even the d orbitals can involve in forming sigma bonds. Right? All the kinds of orbitals, s orbitals, p orbitals, d orbitals, sp, sp2, sp3 orbitals, all the orbitals can involve in forming sigma bonds, involved in doing these kind of linear overlaps, which is on the internuclear axis. Right? This is the first kind of bonds. This is the first kind of bond available with the valence bond theory. Go to valence bond theory. This is the first type of bond can be formed. The sigma bond. Right? Sigma bond. Right? It can be formed by all the type of orbitals. Even with d orbitals, even with d orbitals, you could think of forming a sigma bond, no? So with d orbitals as well. D orbitals as well. No? Sigma bonds can be formed, no? Huh? Right, with the D orbitals. See? This is a nucleus. Or you could think of forming bond like this, no? Right? Or kind of, yeah, even this, right? A D guy mixing with a P guy. Linear overlap. See? The orbital overlap is on the internuclear axis. Right? So ND and NP, another linear overlap. Right? So every kind of orbital is able to come up with these sigma bonds. To form sigma bonds, any kind of orbital can be used. Right? This is the first kind. Right. Then let's discuss about the second kind of orbitals possible. Sorry, second kind of bonds possible, or second kind of orbital overlap possible with the valence bond theory. This is a linear overlap, right? Okay, I'll come with the second type. I'll erase few of these, right? As these things are appearing in your note, right? Let's go to that, right? So the second kind possible when orbitals overlap right outside the internuclear axis. Outside the internuclear axis, right? Outside the internuclear axis, right? Such bonds are referred to as, such overlaps are referred to as partial overlaps and such bonds are referred to as, the bonds formed by partial overlaps are referred to as phi bonds. Right? Let's discuss about that thing as well. Which kind of bonds possible like that? See, right? When two p orbitals are to overlap outside the internuclear axis like this, see, right? When it comes to this one, right? You clearly see this is the internuclear axis, the axis matching the two nuclei, but the orbital overlap happens outside the internuclear axis, no? Partial overlap. This is referred to as a partial overlap. This is the internuclear axis. You won't see an orbital overlap on that axis. It is outside the internuclear axis. That is referred to as a partial overlap. So when these kind of overlaps happens among orbitals, right? Those are referred to as phi bonds. Phi bonds. So kind of a p orbital connects with another p orbital, 2p orbital with another 2p orbital, right? So basically phi bonds can be made, or partial overlaps can be done by p orbitals as well as d orbitals. Only the p orbitals and d orbitals can participate in forming phi bonds. That is very important to note that. This is the internuclear axis. This is the partial overlap. Overlap occurs outside the internuclear axis. See? It could be a p orbital with a d orbital. Right? So that is the second kind of orbital overlap possible. Right? to come up with bonds, come up as a bond, right? So those are referred to as 5 bonds, and keep it in mind, 5 bonds can be made up only by p orbitals or d orbitals. You can't think of a 5 bond formation by a s orbital, huh? So with a s orbital, you can't think of 5 bond formation, because if orbital is involved, always the overlap occurs. Overlap occurs. Even the sp thing like this, no? Always the overlap occurs inside the internuclear axis, right? With s orbitals, you can't think of 5 bond formation. Always the overlap occurs inside the internuclear axis. So you can't think of 5 bond formations from s orbitals or hybrid orbitals as well. Even with the hybrid orbitals, right? You can't think of 5 bond formation, right? So keep that in mind. Very important, right? 5 bonds are formed, or linear or so partial overlaps can be done only by p and d orbitals, right? S and spx, the hybrid orbitals, can't form 5 bonds. So there are 4 types of orbitals now. S, P, D and SPX, the hybrid. So out of those, 5 bonds can be formed only by P and D orbitals, not by SO hybrid orbitals, right? That is very important now, right? So these are the 2 kinds of, right, overlaps which could lead to 2 types of bonds. If the orbital overlap occurs on the internuclear axis, it is referred to as a linear overlap, and such a bond is referred to as a sigma bond. If the orbital overlap of your covalent bond happens outside the nuclear axis, such a overlap is referred to as a partial overlap, and a bond formed like that is referred to as a 5 bond. So all the type of orbitals can involve in sigma bonding, but only the p and d orbitals can involve in partial overlaps and so the 5 bonding. That is, the theory is coming under the VBT. Right now, this is how the bonds are formed 3-dimensionally according to the valence bond theory. Right now, actually, with this theory, right, we can get a clear idea about the strengths of these bonds, sigma bonds and the 5 bonds, as well as, right, which kind of a bond will form first. Is it the sigma or the 5, the first bond between 2 atoms? We can discuss on that as well according to this theory. According to the Lewis theory, both looks like the same, the first bond and the second bond between the 2 atoms. But according to valence bond theory, with the 3D picture, those are with 2 different pictures, right? So it's like this. So like this, no? So let's think of a sigma bond formation, right? Let's think of 2 orbitals, right? Your atom is with these kind of 2 orbitals. Just think of kind of atom. See, like this. Just think of O2, the molecule O2. It comes molecule O2. The 2 oxygens are like this. No? Helium configuration and 2s2, 2p4. That means this is 1 oxygen. Na? The orbitals are like this. Right? We have another oxygen. Two oxygens are there. It is this 2s2 2p4. Two oxygens of O2 molecule. Right? So you clearly see this first oxygen is with these two orbitals with one electron each. Here as well, these two orbitals are with one electron each. So these can be involved in forming covalent bonds. I'm writing these two orbitals. So those are with 90 degrees angles. This is one orbital and this is the other orbital with one oxygen. The second oxygen, right? This is one orbital. This is the other orbital with one electron each. Two orbitals, no? Right? These are the two nuclei. So when the two atoms come closer to each other, when this oxygen come closer to this oxygen, you clearly see first the two orbitals will overlap linearly. First, the two orbitals overlap linearly. When these two guys are coming to each other, coming closer to each other, first you see the overlap of these two things. First, the overlap of these two things occur. So you clearly see the first bond forms by two atoms is always going to be a sigma. Always a linear overlap comes first. After that, after forming the linear overlap, if you are to draw these two guys further closer, then only you are able to overlap these two guys like this partially. First the bond between these two guys happens, then only the bond between these two guys, the partial overlap will occur. So always the first bond formed between two atoms referred to as a sigma bond. Always the first overlap occurs on the internuclear axis. Then only the partial overlap occurs. If you are to further move the two atoms closer to each other, right? So that is next point written in your page number 19. It says always the first bond forms between two atoms is a sigma, right? Then next bonds formed will be 5. There is only one possibility of forming sigma bonds, right? Okay, remember that only one bond can be formed as sigma. Only one bond can be formed as sigma. The other bonds could be 5. That is the next idea, right? So if you take the O2 molecule, right, you can ultimately simply write the things like this. If it comes to O2 molecule, right, the O2, two oxygens will be like this, no? This is a simple Lewis structure. And actually, the first bond between two is sigma. After that, the 5 bond forms. First the sigma, then the 5. Right? So if you think of this kind of Lewis structure, CO2, this Lewis structure is this. right? The first bond out of these, right? The first bond between the two atoms is sigma. Then only the 5 bond forms. Always first bond between two atoms is sigma, then 5 bonds form. Right? Get that idea clearly. So according to Lewis theory, both the bonds are same, looks like same. See, with these diagrams, both the bonds looks like same. But we know those differ, right? According to the valence bond theory, that is the actual existing molecule. If you take the N2, see, Lewis structure looks like this. According to Lewis theory, all the 3 bonds are same. But we know the actual situation is first bond between the 2 atoms is sigma. Next bonds are 5 bonds, 5 and 5. Right? So that is how the bond formation will be discussed by the valence bond theory. Right? Okay? That is about the valence bond theory. And another thing can be explained by the valence bond theory. What is the other thing? So basically, when looking at the Lewis structure, you see both the bonds are same, no? But practically observed, bond strengths of these two guys differ. They have observed that the sigma bonds are more stronger than 5 bonds. Sigma bonds are more stronger than 5 bonds. They have observed that. Let's see. Can we explain that observation with the use of valence bond theory? We can't explain that observation with the Lewis theory, right? Lewis theory gives the same idea with both the bonds, right? But when it comes to valence bond theory, it is the idea is clear. See, if you think of some orbital overlaps by 2 atoms, even in O2, if you think of this orbital overlaps, right? This is one oxygen atom. This is the other oxygen atom. These are 2 oxygen atoms, right? This is one oxygen atom, this is the other one. So you clearly see the orbital overlap of the sigma bond is very high. Orbital overlap of sigma bond is very high, while the orbital overlap of 5 bonds is very small. So actually it is very hard to form a 5 bond as well, no? So when these guys comes closer, the orbital overlap of 5 bond is going to be very low, right? Very low kind of orbital overlap will occur with the 5 bond. See, very little kind of overlap occurring with the 5 bond. But the orbital overlap of sigma bond is very high, so that sigma bonds are more stronger than the 5 bonds. It is very hard to break this bond. It is very hard to break this bond, this one, than this slightly overlapped. So with a little of energy, this will break, this will move apart from each other. So this idea will give you a clear picture about the sigma bond and 5 bond, and with that you can say the sigma bonds are more stronger than 5 bonds. Sigma bonds are more stronger than 5 bonds. It is very hard to break this bond, put these orbitals apart from each other. But it is very easy to break this one, the 5 bonds. Little energy will be sufficient to put these orbitals apart and break the 5 bond. Right? So that is what it says at the next page, the first point. The amount of orbital overlap, right, is high in sigma bond, right, and is low in partial overlap, the 5 bond, right? So that the sigma bonds are more stronger Sigma bonds are more stronger than the 5 bonds. Why is that? Because orbital overlap in sigma bond is greater than the orbital overlap in 5 bond. So that we can say, right, sigma bonds are more stronger than 5 bonds. Right? Those things can be very clearly explained with the use of valence bond theory. Right? This is the picture of the orbital diagram of O2 molecule, right? O2. First bond is sigma, second bond is 5. Right? Okay. Right. That is all you should know about the valence bond theory, right? The sigma and 5 bonds, right? Then we'll discuss about the hybridization concepts, right? Concepts of hybridization and the need of that, right? Okay, you have gained some ideas about how the sigma and 5 bonds are formed, right? Now let's move towards the concept of hybridization, which is also discussed under the valence bond theory, right? Some new concept and very important one, right? Okay. So, right. So let's discuss about the concept of hybridization, right? So as we have done with the explanations of sigma bonds and 5 bonds, right? Now we know how the sigma bonds are formed, how the orbital overlap occurs when forming the sigma bond, and how the partial overlap occurs when forming the 5 bond. We had learned that thing. Now let's move towards the concept of hybridization. Concept of hybridization. First of all, again discuss a bit about why we need to learn this one. What is the importance of the concept of hybridization? Why we need to learn this thing? Can't we explain the bonding without the concept of hybridization? Let's discuss about that. Right? The thing is, let's come up with this thing, Laman. Let's take this example and discuss. Let's take the CH4 as an example molecule. Right? As an example molecule, let's take the CH4. Right. When it comes to CH4, right? Carbon is with this electron configuration. Carbon is with helium 2s2 and 2p2. Carbon is your sixth atom, which is in the group 14. So carbon's orbital diagram looks like this. Carbon's orbital diagram looks like this. Right? So this orbital diagram suggests, the carbon's orbital diagram suggests, right? This carbon can form only two normal covalent bonds. As these are the orbitals with 1 electron each, those are the ones which will participate in bonding, overlaps, orbital overlaps, right? So that the carbons, right, electronic diagram, the Hund's cages suggests that carbon can form only two normal sigma bonds. Carbon can form only two bonds. Let's take two bonds. It could be sigma 5. Carbon can form only two bonds according to this diagram. But we see the existence of CH4. We see the existence of CH4. Now I am trying to explain why we need this concept of hybridization along with the Orbital overlaps. Why we need this concept hybridization? Why we need to learn about this hybridization concepts, right? What this hybridization means and even, right? So when it comes to CH4, right, we clearly see carbon had formed 4 bonds. Carbon had formed 4 bonds. According to this diagram, according to these Hund's cages of carbon, you can't think of forming 4 bonds with this carbon because only 2 orbitals are available with 1 electron each. According to the valence bond theory, the orbitals with 1 electron will overlap with another atom's orbital to come up with the bonds. But here the carbon is with only 2 orbitals, such 2 orbitals. So according to this diagram, carbon can form only 2 bonds. But naturally existing CH4 gives us some hint that carbon is able to form 4 bonds. Right? To explain this, we need the concept of hybridization. To explain this, we need the concept of hybridization. Right? Then next one. If the carbon is to form bonds, if this carbon is to form bonds with the use of these orbitals, the 2p orbitals, these are 2p orbitals, no? This is a 2s orbital, and these are 2p orbitals. So 2px, 2py. So if the carbon is to form bonds with the use of these 2p orbitals, the bond angles between these two things should be 90 degrees. But in CH4, the bond angle they have measured as 109. So the bond angle, to explain the bond angles, or to explain the angles which are not equal to 90 degrees, we need the concept of hybridization. To explain the angles which are not equal to 90 degrees, we need the concept of hybridization. Right? So, and next thing, right? They have found that all of these 4 bonds, that all the 4 CH bond, they have found that all the 4 CH bonds are identical. Scientists have found that all the 4 CH bonds in CH4 are identical. That means same with energy, right? Same with bond distance, bond strength. That is how it looks like. The naturally existing CH4 looks like. Somehow, if all the 4 orbitals are to get involved in forming such 4 bonds, still we can't think of this situation. Why? The 2s guys are with low energy, 2p guys are with high energy. Then 3 bonds should be with high energy and 1 bond should be with low energy. But naturally existing CH4 is with 4 identical bonds, 4 bonds with equal energies. So we can't explain such kind of situation with the normal carbon. If somehow these 4 orbitals are to be used in forming 4 bonds, somehow, right? Yet these are not going to be identical. 3 bonds are with greater energy and 1 bond is going to be with lesser energy. 2 is orbital is less energy than 2p orbitals. Right? So still we are unable to come up with the 4 identical bond situation. Explain that thing. So to do those things, we need the concept of hybridization. Right? So hybridization is actually this. The need of hybridization is actually this. To explain the identical bonds, to explain the identical bonds and the bond angles which are not equal to 90 degrees, in the naturally existing molecule, we need the concept of hybridization. That is the need of learning this stuff to explain the identical bonds, the situation of identical bonds and bond angles which are not equal to 90 degrees. We need the concept of hybridization. Right? Then what this means? What this means? Right? Let's see what this means. Right? First, do this example, and let's come up with the hybridization, that the energy diagram, and then we can come up with good idea what this hybridization means. Right? The need of hybridization is clear now. Right? Let's discuss how this hybridization thing occurs with the CH4. Right? It is like this, Lama. So according to the carbon, the ground state carbon, right? So you have, right? You have, right? 2p stuff and 2s, 2s and 2p. These are the orbitals with the ground state carbon. Right? 2 electrons here, 1 each here. But we now we are clear that you can't form 4 bonds from this configuration. Right? This is energy. Right? So let's discuss about how the hybridization occurs. Let's discuss about how the hybridization occurs. After that, we will be able to clearly define the concept of hybridization. Right? Okay, this is the ground state carbon. We are clear, we are very confirmed that now with this kind of a electronic structure, you can't think of 4 bonds forming. Only 2 can be formed. If you are to think of a kind of a dative bond, you can come up with maximum of 3 bonds. Dative for here and these 2 normal covalents, right? Okay. So actually what happens? What happens is, right? This is all about the gaseous state of the carbon. This is all about the gaseous state of the carbon when the carbon is alone. This is all about the carbon is alone. But actually what happens is, when these hydrogens are coming near to the carbon, when these hydrogens are coming near to this carbon, to form the bonds, when these hydrogens are coming, what happens is kind of electron repulsions would occur. With the carbon and the hydrogens. Right? This is all about the ground state carbon. That means the gaseous carbon when the carbon is alone. This is not about the CH4. This is when the carbon is alone. This electron configuration. But when the hydrogens are coming towards the carbon to form the bonds, what happens is actually the electronic repulsions will occur. Electron repulsions will occur. Because there you have electron cloud here, with carbon even also has an electron cloud here. So 2 electron clouds coming closer, the opposite charges will repel. Similar charges will repel. Electrons have similar charges will repel. So repulsions will occur. Right? When the repulsions occur, what will happen? Right? The energy of the carbon will increase. You know the stuff, no? When the repulsions occur, the kinetic changes will increase, no? When the repulsions occur, particles trying to move heavily, right? So kinetic changes will increase, right? So the carbon's energy will increase when the hydrogens coming near towards the carbon. When the hydrogens are coming towards the carbon, the energy of the carbon will increase, right? So energy of the carbon will increase. So that can be denoted like this electron going towards here, right? It's like this, no? So energy of a particle is high means, energy of a particle is high means, right, the energies of its constituents are high. That is the idea. No? Energy of myself is high means the particles, the constituent particles of myself, those energies are high. The energies of constituent particles of myself is high. That is what it means as the energy of the particle is high. So there, so it's like this, no? So if you have a particle like this, and it is with it is constructed with three particles, right? If this guy's energy is 2 joules, this guy's energy is 4 joules, and this guy's energy is, right, 6 joules, the total energy of this particle is then 12 joules, right? Energy of this blue color particle means summation of energies of its constituents, right? So energy of your whole particle high means the constituent particles are with great energy. Energy of your total particle is low means the constituent particles are with low energy. So with repulsion, what we see is the carbon is gaining some energy. With repulsions, carbon is moving now fastly, speedily. That means carbon is with more energy. Carbon is with more energy means its constituent particles should have more energy. Its constituent particles should have more energy. So with the energy diagram, we should see that. We should see that. That is why I transfer this electron to here. Now this carbon is with a greater energy than this. That is referred to as carbon's excited state. Carbon's excited state. The carbon with great energy. That is happening because when the hydrogens are coming towards the carbon. That won't be there when the carbon is alone. When the hydrogens are coming towards the carbon, that happens. So with this, you have a great energy, right? With this electronic configuration, you have a great energy than this. Are you clear, Laman? Are you clear? Whether this guy is the low energy and that guy is the great energy? Not clear? I think it's clear. If you need, I'll explain a bit more. Like this, no? So let's think that this energy state is with 5 joules. This is the energy state of 5 joules. This is the energy state of 10 joules. Just think of that. Then the total energy of this configuration is, you have 2 electrons at 5 joules. That means 5 joules, 5 joules, altogether 10 joules. And you have 2 electrons with 10 joules, 20 and 30. 5 joules, 5 joules, 10 joules, 10 joules. Altogether, summation is 30. 5 joules plus 5 joules, 10 joules plus 10 joules. Altogether, 30 joules with this configuration. What about this? 1 electron with 5 joules, 3 electrons with 10 joules. Now this total is 35 joules. You see, by doing this kind of electronic movement, you can rationalize the increasement of energy. Here you have 35 joules as a whole, here you have only 30 joules. So this configuration is with a greater energy than this, right? So that is very clear. The carbon's energy is high now because of the repulsions. So it can be denoted like this, right? So that is referred to as the carbon's excited state, right? So one may think now we can form 4 bonds. Now we can form 4 bonds. One may think now we can form the 4 bonds. These 4 bonds can be formed now. One may think like that. But the problem is, still you can't form 4 identical bonds. yes, you can form 4 bonds by overlapping these 4 orbitals, with hydrogens 1s orbitals. Yes, you can form 4 bonds, but the thing is, if you are going for the bonding with this conformation, right, the problem is you are not coming up with 4 identical bonds. You are not coming up with 4 identical bonds, 3 bonds with greater energy and 1 bond with lesser energy. And you are not coming up with 109 bond angles, because these 3 guys are with 90-degree angles, px, py, pz. So if you are to go for bonding with this conformation, this electronic structure, 3 bonds would be there with 90-degree angles. But the naturally existing molecule, you don't have such a bond angle. All the bonds are with identical 109 angle. So the bonding occurred not from this conformation. The bonding in CH4 occurred not from this conformation. Right? So now we need to think of a hybridization. Let's discuss what this hybridization means. What this thing means. Right? So now we are going to give you the idea of the hybridization, right? So this is 2p and this is 2s. Right? So you have this kind of structure, right? So what happens? To come up with 4 identical bonds, and some bond angles not equal to 90 degrees, the only possible way of doing so is actually you need to mix all of these 4 orbitals. You need to mix all of these 4 orbitals to come up with 4 identical orbitals. You have to mix all of these 4 orbitals to come up with 4 identical orbitals. Like this. If not, you can't think of this kind of a 4 identical bonds. The naturally existing form can't be achieved if this won't occur. So as 4 identical bonds are appearing here with the bond angles not equal to 90 degrees, definitely this kind of thing should occur. Mixing of atomic orbitals. Right? Mixing of atomic orbitals. Actually, that is what we refer to as hybridization. Right? This is the hybridization. Right? This is the hybridization. So one can define the hybridization like this: mixing of atomic orbitals to come up with identical orbitals with same energy and shape. Mixing of atomic orbitals to come up with identical orbitals with same shape and energy. So that is referred to as the hybridization. Right? Mixing of atomic orbitals to come up with identical orbitals with same shape and energy. That is referred to as the hybridization. Right? If 1s orbital and 3p orbitals are to be mixed in hybridization, such a hybridization is referred to as a sp3 hybridization. 1s and 3p's are mixed together. So such a hybridization is referred to as a sp3 hybridization. So sp3 hybridization is the mixing of 4 atomic orbitals, 1s and 3p atomic orbitals to come up with 4 identical orbitals of same shape and energy. So these are 4 identical sp3 hybrid orbitals. H2 refers to hybrid orbitals, right? So mixing of atomic orbitals is referred to as the hybridization. Mixing of atomic orbitals to come up with orbitals with same shape and energy is referred to as the hybridization. This is the hybrid state. This is the hybrid state of carbon. Hybridized state. Right now? So now we can think of 4 bonds, 4 identical bonds, and 4 identical bonds which are not with 90-degree bond angles. 4 identical bonds which are not with 90-degree bond angles, because no longer these are px, py, pz's. These are sp3 hybrid orbitals, not the px, py, pz. When the px, py, pz are appearing, definitely those should come up with 90-degree angles, x, y, z axes. But these are not carrying any p, x, py, pz terminages. These are just 4 of sp3 hybrid orbitals. So they can have angles other than 90 degrees, so that we can discuss about the bond angles which are not equal to 90 degrees, right? So that is how the 4 bonds of the CH4 come to the picture, right? So with this kind of a orbital diagram only you can explain completely the bonding in CH4. So hybridization is very needed to do so. Not only the valence bond theory, but some section called as hybridization is needed to completely get the idea of 4 identical bonds of CH4. Right now? So that is the concept of hybridization, right? So always keep it in mind, right? If 4 atomic orbitals are to be mixed to come up with the hybridization, always 4 hybrid orbitals should be formed. Always the number of hybrid orbitals formed is equal to the number of atomic orbitals mixed. Number of hybrid orbitals is equal to the number of atomic orbitals mixed. It should be in line. So 4 atomic orbitals means you have mixed the space of 8 electrons. 4 atomic orbitals means it is the space of 8 electrons. That means definitely you should come up with some orbitals with the space of 8 electrons. That means it should be 4 orbitals. So number of atomic orbitals mixed is going to be same as the number of hybrid orbitals to produce, right? So this is the hybridization of the carbon in CH4, right? Okay, that is all about the hybridization. That is about the hybridization. Then let's discuss about the orbital overlap. The orbital overlap in CH4. This is the hybridization in CH4. Now let's consider about the orbital overlap in CH4. Hybridization in CH4 is clear. Now the orbital overlap in CH4. Orbital overlap in CH4. Right. The idea is this. The orbital overlap in CH4. So we have 4 hybrid orbitals coming from the carbon. We have 4 sp3 hybrid orbitals coming from the carbon. And then those would be looks like this. The 4 hybrid orbitals coming from the carbon, right, would look like this. Right, I'll draw it in red color. I'll draw it in red color here. 4 hybrid orbitals coming from carbon would look like this. You know the shape of the hybrid orbitals, right? Carrying some more p character and less s character. right? So this is the hybrid orbital. 4 hybrid orbitals of carbon. More key pair character is there, you know, when s orbitals are to be mixed, when s orbitals are to be mixed with 3 of p orbitals, then it will give you some 4 of sp3 hybrid orbitals, no? Those will look like this, no? More p character and less s character. This is how the hybrid orbitals looks like, no? We had discussed these things when we are discussing about the electronegativity as well, no? Right? So hybrid orbitals looks like this, right? These are the 4 hybrid orbitals there, right? Those will overlap with 1s orbitals of hydrogen. 1s orbitals of hydrogen. See the orbital overlaps. This is how the 4 bonds in CH4 forms, right? The sp3 hybrid orbitals will overlap with the 1s orbitals of hydrogen. If you know those things in this diagram, we can represent it like this. These are the orbital overlaps. These electrons coming from hydrogen's 1s orbital. Hydrogen's 1s orbital. The green color electrons are coming from hydrogen's 1s orbital. That is how the orbital overlap occurs in CH4. Right? Clear, no? All the pictures are clear, no? This is the energy level diagram of the CH4. This is the 3D picture of the CH4. 3D picture of the CH4. Right, no? So one can represent the same thing in simple form like this. This is the carbon. This is the carbon. No? One can represent the same thing in a simple picture like this. The carbon and 4 hydrogens are there. Carbon and 4 hydrogens are there. And the bonds are actually the sigma bonds, which are formed by orbital overlaps of carbons, sp3 hybrid orbitals with hydrogens 1s atomic orbital. Right now? Okay. So orbital overlap of carbons sp3 hybrid orbital with hydrogens 1s orbital. It's a linear overlap. That is why we say it's a sigma. Those are sigmoids. All the 4 bonds are like this. Carbons sp3, the carbons sp3 will linear overlap with hydrogens 1s. It is clear, right? So that is how the carbons 4 bonds are formed. Those are identical bonds, right? Both are same with the overlap even. Identical bonds, right? With same energy, same overlap, same energy, right? No? That is about the hybridization stuff coming with the carbon CH4, right? No? Okay, so Lama, you can draw this orbital diagram. But I'll give you a few minutes, right? So complete this diagram, or you can take a screen capture as well, right? So just complete the orbital diagram at this page given in page number 20. This page number 20, bottom part, is actually for drawing the orbital diagram here, and at the next page, it is said at the page number 21, the first space, page number 21, the first space, you can draw this one as shown in the about diagram. Mixing of 4 atomic orbitals will lead to mix 4 hybrid orbitals, right? You can draw this one, and at the next space you can draw this one, right? So 3 spaces are given, so just draw the stuff, right? Okay, I'll erase this one. First, at the bottom part of the page number 20, draw these three things, right? This number 1, this number 2, this number 3, right? No? Right now. Okay, just complete stuff or take a screen capture quickly. Right now. So I'll explain this thing again, right? To get the idea, right? Quickly, I'll explain the stuff that we have discussed here, right? So the need of hybridization. This is the need of hybridization is to explain the existence of identical bonds and the bond angles not equal to 90 degrees. We need to come up to the concept of hybridization. That's the first thing, right? Okay. Then what this hybridization means? The hybridization means, right? Actually, hybridization means, right? The mixing of atomic orbitals, to come up with identical, right? Orbitals with same shape and energy. That is what hybridization means. Mixing of atomic orbitals to come up with orbitals with same shape and energy. That is what hybridization means, right? So when that happens, always the number of hybrid orbitals formed will be equal to the number of atomic orbitals mixed to form those hybrid orbitals. So number of hybrid orbitals formed is equal to number of atomic orbitals mixed, right, to give those hybrid orbitals, right? That should be mentioned. And the name of the hybridization is given by considering the amount of orbitals mixed, this and B's, as one s orbital and 3p orbitals are mixed together to give the 4 identical orbitals. That hybridization is referred to as sp3. One s orbital and 3 p's are mixed together. That is why the hybridization is referred to as sp3, right? So then we have discussed the shape of the hybrid orbitals, right? So the s orbital is spherical and 3p orbitals are mixed, so that the shape should carry some greater p character. So some kind of lengthier orbital, that is the shape of the hybrid orbital, right? So such 4 orbitals will be formed as 4 atomic orbitals are mixed, right? As 4 atomic orbitals are mixed, right? As 4 atomic orbitals are mixed, 4 hybrid orbitals should be formed, right? Okay. Then we had came up with the 3D picture of the orbital overlap. So you have 4 hybrid orbitals here written in red color, and these are the 3 orbitals coming from hydrogens, the 1s. So orbital overlap can be referred to as, right, some sp3 hybrid orbitals from the carbon and 1s atomic orbitals from the hydrogens, right? So you can clearly see that with this orbital picture. So this is the shortened form. To summarize the ideas, you can show this thing like this, right? So even in the energy diagram, you can show the orbital overlaps like this, right? So I have used 2 colors, some green color for the hydrogen and red color for the carbons hybrid orbitals, right? No. Okay, then let's do this kind of another stuff, right? This kind of a thing, the same kind of thing to another molecule as well, right? Okay, same stuff. Let's discuss the same stuff with the BH3. Let's discuss the same concept of hybridization with the BH3, taking the BH3 as our example molecule. Let's discuss taking the BH3. Right. Let's see. Now we are referring to molecule BH3, right? Molecule BH3. So BH3, right? So naturally existing BH3 looks like this. 3 identical bonds are there with the existing BH3. 3 identical bonds are there, right? 3 identical bonds are there. 3 identical BH bonds are there with 120-degree bond angles. 120-degree bond angles. That is how the BH3 looks like. This is the naturally existing BH3. Let's use the concept of hybridization to describe this bonding structure. Okay? So when it comes to boron, if you have to consider the boron, which is with helium and 2s2 2p1, boron in group 13, its electron structure looks like this. Electron structure looks like this. 2s and 2p. With the 2s subshell, you have 2 electrons, and with the p subshell, you are with only 1 electron. So electron structure of boron looks like this. This is the electron structure of ground state boron. Right? This is the electron structure of ground state boron. So you can clearly see that you can't form 3 bonds from this electron structure. Only 1 bond can be formed with this kind of a orbital structure. So we could think of another way to come up with the bonding present in the BH3. So actually, when the hydrogens are coming closer to the boron, something happens to this boron. Boron get excited. The energy of the boron will increase. When the hydrogens are coming towards the boron won't appear like this, because this is the ground state boron, which is the gaseous state boron, alone boron. Boron when alone, this electron configuration appears. But when the hydrogens are coming towards the boron, right, what will happen? The boron will get excited. Means boron's energy will increase with the repulsions. So we can denote that excitation or the increasement of energy of the boron by, right, putting this electron to here, exciting this electron to here, so that boron atom is with now great energy than the ground state, than the alone boron. Right? This is the boron's excited state. So one may think that one may think that, right, the three bonds would form from this. But the problem is, if you are to form three bonds with this conformation, the two bonds should be with 90-degree angles. But you won't see such with the existing molecule. All are with 120 angles. And if this form is used to form a bonds, right? So then two bonds are identical but not the third. But with the naturally existing BH3, all the three bonds are identical. So the bonds are not formed by this configuration. So we have to think of the hybridization. So we have to think of kind of hybridization. Right? Now I am referring to the hybridization. Right? So 2p, 2s is there, 2p is there, this is, sorry for that. Right? Then what should happen? To come up with three identical bonds, definitely you have to mix three atomic orbitals. To come up with three identical bonds, three hybrid orbitals should be formed. For that, definitely you have to mix three atomic orbitals. Number of hybrid orbitals are going to be equal to number of atomic orbitals to be mixed, right? So with this, you will come up with sp2 hybridization. sp2 hybridization. 1s and 2p's to be mixed. So sp2 hybridization, and three orbitals, the three hybrid orbitals will look like this with electrons in each. The orbital which is not mixed, with each other will stay at the same level. So this is the sp2 hybridization. Mixing of atomic orbitals, mixing of three atomic orbitals to come up with three identical orbitals with same shape and energy. Is the sp2 hybridization. These are referred to as three of sp2 hybrid orbitals. sp2 hybrid orbitals, right? So now this is referred to as the boron's hybridized state. So with this kind of a orbital picture, we can think of forming three identical bonds with same energy. So if the 1s orbitals of these three hydrogens, are to overlap with the three of sp2 hybrid orbitals, right, then you can think of formation of three identical bonds. That is how the orbital overlap will occur with the BH3 molecule. Right? There is a empty orbital as well, right? There's empty orbital as well. Three bonded pairs, and empty orbital as well. Octet is not there, octet deficient, empty orbital as well. Last day we had discussed about the electron acceptors in Lewis acids. BH3 is kind of a Lewis acid, electron deficient compound, so it can accept an electron pair to its empty orbital. That empty orbital is this. See, so this is the energy diagram of the BH3. This is the energy diagram of BH3. You could clearly see the formation of three hybrid orbitals, the sp3 hybrid orbitals in boron, and this is the orbital overlap with the hydrogens, right? So this is the orbital picture. You can complete this one as the orbital picture of the hybridization, and I'll draw the how this looks like in 3D space, right? So boron coming up with 3 hybrid orbitals like this. Three hybrid orbitals with 90-degree angles. Sorry, 120-degree angles. Right? And those will overlap with 1s orbitals of 3 hydrogen atoms. So these are hydrogens. Hydrogens 1s. Will overlap with borons sp2. Right? So actually those are linear overlaps, right? So you clearly see the orbital overlap comes on the internuclear axis. This is the internuclear axis, which matches the two nuclei of the atoms. The orbital overlap comes on the internuclear axis. 3 sigma bonds, right? So you can draw that thing as well. As a simple picture, you can draw it like this. The BH3. These are 3 identical sigma bonds, where boron coming up with sp2 hybrid orbitals and the hydrogen coming up with 1s atomic orbital. So such 3 bonds are there. Such 3 bonds are there. 3 identical bonds are there with 120-degree angles. Angles which is not equal to 90 degrees. Right? So this is how the orbital picture looks like. Right? So you can take a screen capture here, Lamai, if you complete this stuff, right? This is about the BH3, orbital picture of the BH3. It is coming up with kind of a sp2 hybridization. 3 identical bonds, sp2 hybridization. Right now. Okay. Right. Let's draw for the next one then. This is the BH3. Right now. Took the picture now, right? Right. Let's come up with the next one. The BCl2. Let's draw the orbital picture of the BCl2, the final orbital picture. Let's try to draw this stuff for the BCl2, right? Okay, I copy that. Let's try to draw the orbital picture of the BeCl2. BeCl2, right? So, natural existing BeCl2 looks like this, right? With some 180-degree angle, here, and two identical BCl bonds, two identical beryllium chloride bonds. Right? This is how the BCl2 looks like. How the existing BCl2 looks like. Let's try to copy the orbital diagram, existing orbital diagram of the BCl2. Right? First concern the beryllium, which is the central atom. Always we are drawing the diagram for the central atom. Always we are drawing diagram for the central atom, and always we are referring to the valence shell electrons. We are not referring to any of the inertial electrons here, because the bonding is done only with the participation of valence electrons. Only the valence electrons are used in bonding, right? So we are considering only the valence electrons of the central atom, right? So hybridization is always happening with the central atom only, right? Okay. So the boron, your boron, the beryllium is central. Looks like this. Beryllium is with helium configuration and 2s2. That's the beryllium's configuration. So if you have to think of the orbital picture of the beryllium is energy, right? The ground state configuration, right? It looks like this. Only 2s2 is appearing. It is group 2 element. This is the boron's ground state, right? So definitely we are unable to form two bonds with this kind of configuration. Definitely we need to think of another method, another way. So what happens when two chlorines are coming towards the beryllium is, actually beryllium gains some energy due to the repulsions, and we can denote it by transferring this electron to here, transferring that electron to here, right? So that is referred to as the boron's excited state. Boron's excited state. Right? So with the boron's excited state, you are with one electron at 2s and one electron as 2p. Boron's excited state. Right now? So we can form two bonds from this configuration, but the problem is, if you are to make two bonds from this, those bonds are not going to be identical with the energy. Two different energies will appear with these two bonds. So that we should think of a hybridization. We should think of a hybridization. Mixing of atomic orbitals to come up with identical hybrid orbitals. So as two identical bonds are needed, we need two hybrid orbitals. That means only two atomic orbitals are to mix are to be mixed. So it is going to be a sp hybridization. It is going to be sp hybridization. If you are to mix only two atomic orbitals, right, it is going to be one coming from this, the other coming from the p, sp hybridization. So this is a hybridization. It is kind of a sp hybridization. So with that, you will get two identical orbitals with same shape and energy. sp hybridization. Right? Okay, I'll write it in red color, no? So hybridization, hybrid orbitals, no? With one electron each. Two of sp hybrid orbitals. So if only two atomic orbitals are to be mixed, only two hybrid orbitals will form, right? Okay, and then you have two non-hybrid orbitals as well. These are not mixed, so those two things will appear there. So this is the orbital picture of the hybridized beryllium. Hybridized beryllium. Then you can think of forming two bonds, to forming two identical BCl bonds by overlapping the chlorines orbitals with these two hybrid orbitals. What are the chlorines orbital? What are the chlorines orbital involving here to form the bonds? Which orbital of chlorine involves to form the bonds here? Basically, when it comes to chlorine, it is with this kind of a configuration. Neon and 3s2, 3p5, 3s2, 3p5. This is how the chlorine looks like. 2, 3, 4, 5. See? So that chlorines, this orbital is there. This is the chlorine's orbital involved in orbital overlap. This is the chlorine's orbital involved in orbital overlap. That is 3p, that is kind of a 3p orbital. So chlorine's 3p is the one to participate or the one to overlap with the hybrid orbitals of beryllium. Chlorine's 3p. So from the corner terms, right? The last occupied subshell, the last occupied orbital or subshell should be written like this. Last occupied subshell, orbital from the last orbital occupied subshell will involve in orbital overlap from the corner atom. From the central atom, the hybrid orbitals are involved in forming bonds for the sigma bonds, right? From corner atoms, last occupied, some orbital from last occupied subshell should involve, right? So that is how the two bonds are formed by overlapping of hybrid orbitals and atomic orbitals. If you need to come up with the 3D picture, if you wish to come up with the 3D picture, right, it looks like this. Two hybrid orbitals from beryllium. This one hybrid orbital from beryllium. This second hybrid orbital from beryllium. Two sp hybrid orbitals from beryllium. linearly overlap. The first bond is sigma no always. First bond is sigma no. Linear overlaps with 3p orbitals of 3p orbitals of see 3p orbitals of chlorine. Chlorine's 3p. 3p orbitals of chlorine. But I'll draw like this. No, it's better now. 3p orbitals of chlorine. Two 3p orbitals of chlorine will overlap with beryllium's hybrid orbitals. 3p with beryllium's sp hybrid orbitals. sp hybrid orbitals. This is the 3D picture of beryllium chloride. So you see, this overlap occurs. This overlap occurs inside the internuclear axis. Inside the internuclear axis. Right? This is the internuclear axis, matching the chlorine and beryllium. On that, the overlap occurs. 2 sigma modes. 2 sigma modes. Right? 2 sigma modes. So one can note that thing like this. Beryllium is appearing with 2 Cls. So this bond is kind of sigma. First bond between 2 atoms is actually sigma. Right? Which is formed by overlapping of beryllium's sp hybrid orbital with chlorine's 3p atomic orbital. AO means atomic orbital. That is how the 2 bonds are formed. Right? Those are with 180 bond angle. Right now, this is all about the bonding nature of BeCl2, beryllium chloride. Right? Let's complete the diagram now. Right, no? So we'll come up with another molecule, very special one. The NH3. Let's do the same kind of procedure for NH3. Right? Let's do. So at home, just try to draw these things now. So you have got some idea now, no? So make sure you alone can draw these diagrams without the help of me, right? You should be able to draw these things. So at home, just try to do, repeat the same. See whether you can do so. Right? I have described you, know. I have teach you, know, how to do this thing. Right? Then definitely try to draw by your own these diagrams. Those will be asked in your first term test papers, right? Okay. Right. Let's try to draw the orbital picture for the NH3. right? And see why we use the hybridization, why we need the hybridization to explain the bonding in industry, right? Okay, right. Let's copy the industry then. Right. So I am doing more examples now, so right. So as we have some limited time, right, I am trying to do more of examples so that you can try at home, right? So we will send you the video as well, so you can take screen captures, right, and complete the notes, and you can see the video as well again and get the ideas clearly, right? As you are participating in the class live to the live sessions, right, you can quickly go through the videos, right? I prefer you to see the video once again, just with 1.5x or with 1.75x with that speed, 1.5 or 1.75. You can watch the video again, YouTube video, right? Quickly go through that again. Then the ideas will be confirmed, completed in your mind, right? As you have participated in the class here, so some things are there in your head, no? Right? So quickly going through the video again will confirm the ideas in you. Do that as well after you receive the video. But always just look at the video once, right? That will be very helpful. Just go through quickly. No need of watching the video with this normal speed. Right? Just go through quickly the video. Always watch that. Right? That will be helpful for you. Right? So let's come up with the industry. Let's come up with the industry. Right? So industry. So naturally existing industry looks like this. It's a 3D structure, am I? 3D structure with some 3 identical bonds. Three identical NH bonds with kind of 106.5 bond angles, right? This is the existing nature of NH3. Let's try to describe or clearly understand the bonding in the NH3, right? When it comes to nitrogen, it is with the helium configuration and 2s2, 2p3, this group 15 element, right? So the ground state with the ground state nitrogen, the electron configuration would be look like this electron arrangement. Right? This is 2s, this is 2p, this is energy. Right? This is the ground state electron arrangement of nitrogen. So one may think with this form you can come up with 3 bonds, 3 identical bonds. Yes, that is true. with this form, even with this form, you can come up with 3 identical NH bonds. 3 bonds with same energy. But the problem is the bond angle. If you are to come up with 3 identical bonds from these 3 orbitals, involving these 3 orbitals, orbital overlaps, the bonds, 3 bonds should be with 90-degree angles to each. This px, py, pz, which are along those x, y, z axes. So that means 90-degree angles should be there among those. But the existing nitrogen is with other idea. It is with 106.5 bond angles, which is not equal to 90. So we have to think of the hybridization and the concepts. So this is about the ground state nitrogen, the nitrogen alone, the gaseous state nitrogen or the nitrogen when alone. But when the 3 hydrogens are coming near to the nitrogen, the repulsions occur, energy of the nitrogen will increase. We can denote, or we can explain that increasement of energy by exciting this electron to here, right? So I'll just excite the electron to this other orbital. Both are okay, no worries, huh? No worries. But I'll just excite here. No worries, even though you have put here. No worries, right? So then it would be looks like this. So take this idea, right? When you are to excite this thing to here, right? It will look like this, right? According to Hund's rule, the things are okay, right? First 3 electrons are with same spins. Then when you are to couple, it should come up with the opposite spin, anti-parallel, right? This is how the nitrogen looks like in the excited state. Now we have problem. Now you don't have 3 identical bonds. Now you don't have 3 identical orbitals to come up with 3 identical bonds. Definitely we need to consider kind of hybridization. Definitely we need to consider the kind of hybridization, right? So hybridization is needed. Hybridization is needed. Right? Hybridization is needed. So, right, one can mix only these 3. For 3 identical bonds, one can mix only these 3 guys, right? But the problem is only these 3 are to be mixed to copy the hybridization. It is going to be a sp2 hybridization, sp2 hybridization. But when it comes to sp2 hybridizations, right, the bond angle is more closer to 120. Bond angle is more closer to 120 in sp2 hybridization. We had seen that with the BCl3, with the BCl3, we had seen that when the sp2 hybridization occurs, bond angle is closer to 120. That is not good. Here, the natural existing NH3 is with a 106.5 bond angle, which is actually closer to the 109, than the 120, than the 120. This value is more closer to 109, which comes with the sp3 hybridization. If the sp3 hybridization occurs, right, earlier with the CH4, we had seen that when the sp3 hybridization occurred with the CH4, the bond angle was 109. When the sp2 hybridization occurs, we had seen that with BCl3, the bond angle was 120. So this value is more closer to the 109 than the 120. So better to go with the sp3 hybridization then. sp3 hybridization then. So in NH3, the hybridization is sp3, sp3, not the sp2, not the sp2. It should be sp3. Right? The hybridization is sp3. So that you will produce 4 identical orbitals. 4 identical orbitals, but one orbital is completely filled and 3 orbitals are there with 1 electron each. You're producing 4 identical orbitals, 4 identical sp3 hybrid orbitals, because 4 atomic orbitals are mixed. Definitely you have to come up with 4 identical hybrid orbitals. Number of hybrid orbitals should be equal to the number of atomic orbitals, right? And here, one orbital is completely filled and 3 orbitals are there with 1 electron each. So those 3 orbitals can be used to form those sigma bonds, tree of sigma bonds. Right? This is the nitrogen's hybridized state. Right? So these 3 can be used to form those 3 sigma bonds with those hydrogens, with the overlap of hydrogens 1s orbitals. So these are the hydrogens. So these are the red color things are the, these 3 red color things are the nitrogens hybrid orbitals involved in forming sigma bonds. And what is this? This is very important. What is this? This is the nitrogens lone pair. This is the nitrogens lone pair. This is the nitrogens lone pair. Right? So that we can conclude the sigma bonded electrons of the central atom and the lone pair electrons of the central atom belongs to hybrid orbitals. That is a very important observation. All the sigma bonded electrons and the lone pair electrons of the central atom belongs to hybrid orbitals. That is what we see, and that is what we need to grab from this diagram. Right? This is what? This is nitrogen's lone pair. Right now? So the sigma bonded electrons as well as the lone pair electrons belongs to hybrid orbitals. Right? So this gives you a very important conclusion. What is that? Now, by just calculating the sigma bonds, sigma pairs and lone pairs, the summation of sigma pairs and lone pairs should give you the hybridization then. So as the sigma bonded electrons and the lone pair electrons of the central atom belongs to hybrid orbitals, the opposite of that is, by coming up with the sigma bonded electrons and the lone pair electrons, you can comment on the hybridization. See, number of sigma bonds and the lone pairs are equal to 4. 1, 2, 3, 4. That means the hybridization should be, 4 hybrid orbitals should be there, so that the hybridization should be sp3. That is very important. So that by just looking at the molecule, you can comment on the hybridization by counting the number of sigma bonds and the lone pairs. because the sigma bonded electrons and the lone pair electrons belongs to hybrid orbitals. So this says you have 3 sigma bonds and a lone pair 4 units. That means 4 hybrid orbitals should be there. That means the hybridization should be S and 3 P's, sp3, sp3, right? So that is very important conclusion ultimately. So we can come up with the orbital picture as well. We can come up with the orbital picture of the ammonia. So it would look like, the 3D picture would look like, right? These are the sp3 hybrid orbitals appearing with the nitrogen. sp3 hybrid orbitals appearing with the nitrogen. And these are the free oneness orbitals coming from hydrogens. The oneness of hydrogens. Linearly overlapping with sp3s of nitrogen. And keep it in mind, this lone pair also belongs to sp3. The lone pair is also, it belongs to sp3. Lone pair. Lone pair is also belongs to sp3. That is very important. Right now, that is the orbital picture, the 3D picture of the ammonia. If you have to simplify the same diagram, it can be represented like this. Right? This bond is actually a kind of a sigma bond, which is formed by the orbital overlap of nitrogens sp3 hybrid orbital with the hydrogens oneness atomic orbital. Right now? And these things are with (109) bond angle. Sorry, 106.5 bond angle. That is how the industry looks like. Right now? Just complete the picture now. So you can take a screen capture, Lama. Just take a screen capture. Right? So with this, we had came up with a very important conclusion. That is very important, nah? What was that important conclusion? That important conclusion was, I'll write like here, right? Number of sigma bonds and lone pairs that count will give you the hybridization of the central atom. Number of sigma bonds plus lone pairs that count will ultimately give you the hybridization of the central atom. Very important conclusion. See, if that count is equal to 2, that means you have two hybrid orbitals. Two hybrid orbitals, because the sigma bonded electrons and the lone pair electrons are inside hybrid orbitals. If that is equal to 2, you have two hybrid orbitals. That means one s and one p atomic orbitals should be involved in forming those two hybrid orbitals. If that count is 3, then sp2. If that count is 4, then sp3. Right? So number of sigma-bonds and lone pairs that count will give you the hybridization of the central atom. Right? Idea is very clear. If it is going to be 5, it should be sp3 and d, sp3d. If it is 6, it is sp3d2. Right? Those are not in the A-level syllabus, but these three things are there. sp3d and sp3d2 is not asked, right? But you can, with the trend, you can think of those as well, right? So write this thing as well, right? Complete that thing. Right now, okay, with the use of that knowledge, right, let's try to come up with some complex structure, some hard stuff, right? At the next page, you see the H2O is there and the NH4 plus is there, right? I thought of drawing the NH4 plus. Just do the H2O at home. Just do the H2O thing at home, right? Some homework for you. Just do the H2O thing at home and send me the answer. Send me the answer as well, right? So I'll give you some idea about the NH4 plus. NH4 plus. That's some kind of hard stuff, right? So give you idea about the NH4 plus. With the use of this knowledge, we can very easily draw the NH4 plus. See how to come up with the NH4 plus with this use of this thing, right? Okay, let's come up with the NH4 plus. Right. Let's draw the energy diagrams of NH4 plus. NH4 plus. So now my NH4 plus looks like this. Plus charge on the nitrogen. So you have 4 identical NH bonds with normally 109 bond angle. It is how this looks like. Actually existing NH4 plus looks like, right? So when considering nitrogen, it is group 15, so that it is with this kind of a configuration as it is group 15. But here, see, this is not the nitrogen at the center. It is not the nitrogen at the center. It is the N plus. It is the N plus at the center. So your central atom is, or the central species is N plus, not the nitrogen. So we have to consider N plus. You have to consider N plus when coming up with the energy diagrams. So with the N plus, you are with only 2 s electrons and, sorry for this, it's 3 now. 2 s electrons and only 2 p electrons. N plus, no? N plus means you have to release one of the electrons from here. N plus. So this is your central atom. So this is how the ground state of N plus looks like. So let's draw. Let's draw the energy diagram. Right? So you have 2s and 2p. This is energy. So with the 2s, you have 2 electrons. With the 2p, only 2 electrons are there. This is the N plus ground state. Then, when the hydrogens are coming close to the nitrogen, right? Nitrogen gets excited, increases its energy. That means we can denote that by exciting this electron to here. We are not adding this electron to here, right? It should be go to here. According to Hund's rule, one by one, the electrons should occupy singly to the maximum. Singly to the maximum. That is why I put the electron here, not coupling with the existing stuff. So Hund's rule, Pauli's exclusion principle, those should be okay, right? With the electron transients, right? So with this, you will come up with the excited N plus, the excited N plus, right? Looks like this. The N plus excited state. Then after coming to this state, just use the theory we have just learned. Just use the theory we have just learned. By counting the sigma bonds and the lone pairs, you can come up with the hybridization of the central atom. So here you have 1, 2, 3, 4. 1, 2, 3, 4. 4 sigma bonds and no lone pairs. So the hybridization of this thing should be sp3. Altogether 4 units. 1, 2, 3, 4. Sigma bonds and lone pair, the count is 4. That means 4 hybrid orbitals should be there. That means the hybridization should be sp3 to form the 4 hybrid orbitals. 4 atomic orbitals should be mixed. That is sp3 then. So very easy now to compare, to consider hybridization by just adding the sigma bonds and the lone pairs. So that is the hybridization, right? Just the sp3 that means you are supposed to come up with 4 identical orbitals, right, with same shape and same energy. Four of sp3 hybrid orbitals, right? So this is the hybridization, the sp3 hybridization. And this is the N plus hybrid state, right? So now we can think of the orbital overlap. The 4 hydrogens, the 1s electron densities of the 4 hydrogens will overlap like this, the linearly. The first bond is sigma, linear overlap. Right? This is the energy diagram of the NH4 plus. Of the NH4 plus. So if you are to draw that, right, the things will appear like this. These are the 4 sp3 hybrid orbitals. Right, of nitrogen. Those will linearly overlap with the spherical 1s orbitals of hydrogen. Hydrogen is with 1s 1, no? The electron is with inside 1s orbital, no? So this is the stuff. Hydrogen's 1s linearly overlap with nitrogen's sp3s. Actually not nitrogens, no? It is nitrogen plus sp3s. Right? If you need to copy the simplified diagram, it would look like this. Nitrogen plus is there. So right, you can write the sigma bond is formed by linear overlap of nitrogen plus guys sp3 hybrid orbital with right hydrogens 1s atomic orbital. And that is how this orbital overlap occurred to form those sigma bonds. And this bond angle is 109. This is about the initial plus. See. Right now. So complete diagrams. So I'm always trying to give you more examples, right? So that you can work at home as well. So I'll give you some 2 homework things as well. So just draw these things and send it to me. Send those to me. Right? Right. So you can take a screen capture as well, right, to complete the notes quickly. So just do for the H2O at home and for the H2O plus as well. Some homework. Draw these pictures for the H2O and the H2O plus as well. Right? H2O plus as well. Is right? So you can draw pictures now. By just calculating the sigma bonds and the lone pairs, you can think of the hybridization of the central atom. By just calculating the sigma bonds and the lone pairs, you can come up with the hybridization of the central atom. So with the use of those, just draw for H2 and H2 plus. Right? Okay? Right. Actually, this is all about the sigma bond. The orbital overlaps of sigma bonds. Orbital overlap of sigma bonds. So actually sigma bonds can be made by any kind of orbital. from s orbitals, p orbitals, as well as hybrid orbitals. We had seen that. This is a sigma bond formed by s orbital and hybrid orbital. So with the BeCl2, beryllium chloride, we have seen that sigma bonds forming with hybrid orbitals as well as with p orbitals, combining those. Right. Now let's go to towards the phi bond. Right. Let's discuss about the phi bond as well. The orbital overlap, the orbital pictures in phi bonds, the engineer diagrams in phi bonds. Okay, consider that as the final section for today. Orbital diagrams in phi bonds. Right, that is at your page 25. Let's come up with the CO2 as our example. The CO2, the bonding in CO2. Right. Let's consider the phi bond situation. Right. Phi bond. Phi bond. Orbital overlap of phi bond. Right. Let's come up with the CO2. CO2. Right. Consider CO2. Right. So CO2 looks like this. CO2 looks like this. Right. You have a 180 bond angle. Right. So the first bond is sigma. First bond is sigma. Right. And second bond is phi. Right. That is how CO2 looks like. Huh? So you have two identical bonds. Two identical bonds. Right. With the CO2. Okay. Right. Let's discuss about phi bond. Right. What we know is what we learned at the beginning of the lesson today is actually phi bonds can be made only by NP or ND orbitals. So phi bonds can't be made by hybrid orbitals, can be made only by P or D orbitals. This NP means 2p, 3p like that. N means the valence shell, final energy level. Right? That is some idea we know. Right? So let's come up with the orbital diagram or the engineer diagram of the CO2. First the carbon. Carbon is kind of a group 14 element. Right? It is actually sixth element of our periodic table. So the configuration looks like this. Right? So let's come up with the engineering diagram of the carbon. Two S and two P are there. Right? So with the 2s, you have 2 electrons. With the 2p, you have 2 electrons with the carbon, according to the Hund's rule. And the Paulus is below the stuff, right? So this is carbon's ground state. Right? Then when the oxygens come close to the carbon, what will happen? The carbon get excited, so will increase its energy. We can denote it by exciting this electron to here. Right? So you would come up with this kind of a electronic structure. Sorry for this, right? That is it. So 4 orbitals are there. So we can think of forming 4 bonds using these 4 orbitals. This is the excited state. This is the excited state, right? So then what we can say? So after this stage, just think of the hybridization. Right? So the count of sigma bonds and the lone pairs of the constituting atom, the central atom, will give you the hybridization. Around the central atom, you have only 2 sigma bonds, no lone pairs. 2 sigma bonds, no lone pairs. That means only 2 units are there. 2 sigma bonds, no lone pairs. So the count, the summation is 2. So 2 units means, right, 2 hybrid orbitals. That means just the sp hybridization. So as a hybridization, you have to perform a sp hybridization, right? So it would look like this. See how easy. As we know the hybridization, as we can come up with hybridization with use of the sigma bonds and lone pairs, right? So these two will get hybridized, mixed together to come up as hybrid orbitals, right? So this is the orbital picture then. 2p, 2s will appear, and the 2 hybrid orbitals formed by sp hybridization will appear like this, right? These are 2 sp hybrid orbitals, right? So this is the carbon's hybrid state, and there are another two orbitals which haven't undergo the hybridization. So those two also appear as the same place as in earlier. So this is the hybridized picture. This is the how the carbon's orbitals look like after the hybridization, right? These are referred to as non-hybrid. Right? 2p orbitals. non-hybrid 2p orbitals, and these are the two sp hybrid orbitals. So to form the sigma bonds, right, the oxygens electrons will overlap with these oxygens electrons will overlap with these to form the sigma bonds. To form the 5 bonds, right, the oxygens electrons will overlap with these to form the 5 bonds. Right? These are things involved in sigma bonds. These are things involved in pi bonds. So oxygens which orbitals? Can we come up with those? When it comes to oxygen, right? When it comes to oxygen, right? Its electronic structures looks like this: helium and 2s2, 2p4, 2s2, 2p4. See, 2p4. You clearly see there are two orbitals available. There are two 2p orbitals available to form sigma and 5 bonds. For this oxygen, to form a sigma and 5 bond, two orbitals are available. This can be used to form the sigma bond, and this can be used to form the 5 bond. Those are 2p atomic orbitals. Right? The orbitals at the valence at the outermost subshell. The orbitals at the occupied orbitals at the outermost subshell, the 2p's. Right? With this oxygen, right? This sigma bond will be produced, and this 5 bond will be produced. With the other oxygen, this sigma bond will be produced, and this 5 bond will be produced. If you are to mark these things 1 and 2, let's take this one as 1, this as 2, and this is 1, this 2. This oxygen 1, this 2. 2 sigma bonds, 2 5 bonds. Right now? So that is how the orbital picture looks like. Right? This is some extra stuff, right? No need to draw this one. The oxygen thing. Right? This is enough. So this is how you produce the 5 bond. So if you are to come up with some simplified picture, right? I can draw the simplified picture like this. I'm not going to draw the orbital diagram. I'm not going to draw the 3D picture. Just this is enough. Right? So you have sigma bonds as well as 5 bonds. Sigmas as well as 5 bonds. Right? For the sigma bonds, right? The central atoms hybrid orbitals. The carbons sp hybrid orbital. will linearly overlap with the oxygen's 2p atomic orbital. Central atom's sp hybrid orbital will linearly overlap with oxygen's 2p atomic orbital. How to produce this? Phi bond. It will be produced by carbons, central atom carbons, but non-hybrid 2p orbitals. Non-hybrid. To be non-hybrid, we'll write it like this. Central atoms 2p, not the hybrid, non-hybrid. Non-hybrid orbital partially overlaps with the oxygen's 2p atomic orbital. Non-hybrid orbitals are the orbitals which appear in a hybridized atom. Non-hybrid orbitals are the orbitals which will not undergo the hybridization in a hybridized atom. That is, those are non-hybrid orbitals. We label that those things as non-hybrid orbitals, as those are the orbitals which haven't undergo the hybridization in a hybridized atom. So those are the ones involved in forming phi bonds. Right? These are things involved in sigma bonds. Right now, that is how the phi bond is made. Just by p orbitals, p orbitals, symmetric orbitals, po symmetric orbitals, only you are able to come up with phi bonds. Right? Phi bonds only by po orbitals, no? Phi bonds by just po. Only by just p orbitals you can form the phi bonds. See? Like this. Right? That is the idea. So complete this one quickly. But just take a screen capture. Complete. Right. Okay, now you can take a screen capture here, right? So just complete note for the phi bond. හරිද? ඒක තමයි phi bond එක කතාව. Always remember, right? Phi bonds can be made only by p or d orbitals. That is very important. Right? Okay, no? So this is all about the orbital overlaps. Right? Okay. So with this, let's wind up for today. Right? So with the next lesson, we'll come up with the Vespa theory. Right? The shapes of the molecules. Right? The electron pair geometries, the shapes and the stuff. We'll discuss about those things in the next class. So we'll wind up at this stage. So just do the homework and complete this stuff and see the video again. Right? Okay. So goodbye then. Good night. See you next week.